Now, if acceleration of an object moving around a circle at constant velocity is always toward the center, or centripetal, then the question arises, how much work is being done by the net force acting on that object? Well, if its acceleration is centripetal, then the net force is equal to the mass times acceleration. So I'd better write that down. Let me go off camera for a second. It then follows that under the conditions of this problem, which entail constant velocity on a circle, that the acceleration is equal to the centripetal acceleration. There's no acceleration in the direction of motion, only the centripetal acceleration perpendicular to the direction of motion, so that our net force is our mass times our acceleration. Our acceleration is our centripetal acceleration. And the centripetal acceleration has magnitude mv squared over r, and it's toward the center. So we have a net force of mv squared over r toward the center. Again, this applies only in this case of a uniform velocity, uniform speed around a circle. It follows that if the velocity is, and it could be in any direction, at some point on the circle, the velocity will have any direction you might want to choose. So we take a velocity at some arbitrary point on the circle. The velocity and centripetal force are perpendicular. Now, if the velocity and the centripetal force are perpendicular, then for any very short time interval, the change in position divided by the centripetal force are perpendicular. So I'm going to draw those vectors. For any short time interval, for small delta t, meaning a short time interval, then our delta s is going to be very nearly in the same direction as our v. Now, in even a short time interval, our velocity, since we've moved a little ways around the circle, even in a very short time interval, our velocity will change direction very slightly. But for small delta t, the angle between our delta s and our f net will be very close to 90 degrees, because our direction of delta s will be very close to the direction of v, which makes a 90-degree angle with the centripetal force. And then, as we let delta t approach zero, we find that delta s approaches perpendicular. Now, what's the implication of delta s being at or very close to perpendicular with centripetal force? What's the implication for the work done? Remember that the work is just the dot product of your centripetal force with your delta s. So, well, the implication for the work done then is that the work done on a small time interval is equal to f net times delta s, or the dot product of f net with delta s. Now, how do we do the dot product of two vectors? We project one vector onto the line of the other, and then we multiply the projection by that other vector. Now, I've got a pretty small picture here, but hopefully you can see it. I've got two vectors here that make almost but not quite a right angle. So that if we project this vector onto the line of this vector, we project from the tip down to that line, and we get a very small projection. So here is our projection. And we multiply that projection by this vector. We're going to get a negative result since the projection's in the opposite direction to the vector. Now, what if this angle here gets closer to 90 degrees? What happens to that projection? It gets smaller. And it keeps getting smaller until when the vector makes an angle of 90 degrees, the projection shrinks down to zero. What does that do to the dot product? That makes the dot product zero, meaning that the work would be zero. If the delta t is not quite zero but very close to zero, then the projection is going to be not quite zero but very close to zero. So the dot product is going to be almost zero. If we keep letting delta t shrink down to 0. If we let delta t approach 0, then the projection is going to approach 0 because the angle is going to approach 90 degrees. As the projection approaches 0, the work done by the net force approaches 0. Our conclusion is that a centripetal force does 0 work on an object moving around the circle. Now I've written this out as W net equals F net dot delta S approaches 0, so the centripetal force does 0 work. I just squeeze that word work in there pretty tightly, so you might not be able to read it, but that's our conclusion. Now there are subtleties to this argument, and there are questions that could arise from this argument. And if you understand calculus, which of course is not a prerequisite for the course, you might understand what some of those subtleties are, but for right now we're going to gloss over them and just accept this argument, which ought to be fairly convincing, that the centripetal force does 0 work on the object moving around the arc.